No.
Okay, so just before the break, we got to the point of discussing the various ways we can use the Atmel UseArt to communicate with other devices. And the example I want to really sort of get across to you most importantly is using the PC as a means of either I/O or diagnostic, which is essentially the same thing, but one is used as part of the application. The other use is really just to check the application is working properly and get, use it as a kind of test equipment. So this example I'm showing you here could be considered either of those. What's happening is the Atmel is running a program, which if I just minimize that, the Atmel is running a program which is called, which one is it? That code is called UseArt. That's it here, UseArt 2560C, and you've got this in your sample code archives. And you see I've written into the code the configuration we want. This, where it says flow control hardware, you can actually put none and it will work just as well. In fact, I prefer none really these days. When I wrote this, I had hardware here, but from the hyperterminal end, it works with none. And in fact, it's in the UseArt configuration, it's none. Basically, in order to understand what this does, we set up the UseArt. I'm going to go through that quickly with you in a moment because we've already seen in the lecture slides the way the registers are used, but we'll have a quick look at the actual code to set up the UseArt and set up the ports we need, and then send a display banner to the PC. In the remaining slides, by the way, in the lecture, if we just go to where we were, the last slide we were at when we had a tea break. The rest of the slides are really just looking at code, okay, which is in the sample code I'm going to show you. So I suppose it's probably easier if I show you the code on the slides because it's in larger fonts, but it's the same code that we have in the program. So I'll do this. You notice that the while loop has nothing in it. Everything here is driven by interrupts once we have it running. We're not transmitting anything here, okay? And initialize general only is setting the interrupts enable. There's no direct port configuration in there because the UseArt, when you configure the UseArt, it automatically takes over the transmit and receive pins that are associated with it and converts them into a transmit and receive pin rather than an I/O pin. So we sort of implicitly are taking over those pins. We don't need to do anything in here. Again, I'm not going to go through every word here. This kind of slide, you need to study it yourself to make sure you fully understand all the configuration. You also have the information in the manual and the lecture that's just preceded this that give you details of what's going on here. But I will briefly take you through. We've got these 3 control registers, and basically we've got to set up the way that the UseArt works. And we're going to double the speed, that special clock setting I mentioned for to allow us to get the timing. It basically reduces the error of the bit rate timing because we're dividing from 1 million. We're trying to get down to 9,600, which you can't get a perfect division of it. 1 million divided by something, there's no number that gives you 960. It's going to be a fractional value. So we want to have the minimum error from that we can get. So by but basically this is like a little adjustment we can make which helps us reduce the error, and you need to read the manual to fully understand that. But to operate it, you don't need to understand it. You just use the way the sample code is set and it will work fine, okay? But look at the manual if you really want to understand what's going on there. This is more important because here we are setting the various interrupts we're using and enabling the various parts of the UseArt. So we are saying we want the receive interrupt enabled, but not the transmit one or the data register empty one. We just want the receive interrupt. And we want to turn on the receiver and we want to turn on the transmitter. And this code here is for 8 bits of data, not 9 or not 5 bits, etc. We want 8-bit data. So this is an important configuration here. And here we are setting that we are using asynchronous mode, and we are setting the parity to be no parity, which is these 2 bits here. And we are setting 1 stop bit. And then these are also part of the 8-bit data configuration. And then this is the clock polarity, which doesn't really matter because we're using it in asynchronous mode anyway. And this is the calculation for receipt to divide the 1 million clock, but to get 9600. And bearing in mind, we've got this other value set here. There's a lookup table which you can basically get that value from, and with the clock doubler there, and I'll let you look it up in the table in the manual if you really want to know how I got that. But if you just use this value, it will work perfectly well with 9600 board, which is what we're going to be using. That I found that works with quite a few of the sensors that you might want to connect to as well, like our RFID readers as well as the USART and so on. So this value tends to be in several of my sample programs. And then the code itself, it's all really in the receive loop, okay, in the interrupt. So what happens is when a byte is received, it will come into this simple bit of code here, which says, if I received a 1, character 1, and we need to have a look at ASCII, we'll be looking at that later in the lecture. If we received a 1, display this, and then if we received a 2, display this. So this is sending back to the PC. So the PC is sending these values, and the Atmo is sending these values. So we have two-way communication. Now, of course, instead of printing this message back to the PC, if I send a 1, I could turn on a motor or turn on a light or something. So I could remote control something. I don't have to, anything could go here. And same, when on the PC end, instead of just displaying this, I could do something, store the data in a database or something. So this is just an example of the communication, but what you actually do when you receive these controls is up to you. So this is like an ability to build two-way communication, but it could also be that you just send values to diagnose what's going on in your program. So each part of your code in your Atmel, you could send a different message to the PC, so you can see you've reached different parts of your program, like a kind of diagnostic tool. Okay. If you look here, to transmit a string, I need to send each of these bytes separately. So to send a string, I'm going to go through the data as a string, as an array of characters, actually. And for each one of them, I'm going to transmit a single byte, which is this other bit of code here I'll come to in a minute. And when I've transmitted that whole row of single bytes, I'm then going to transmit a special character called a carriage return character, which will cause the cursor to go back to the beginning of the screen, to the left-hand side. And then I'll transmit a special character line feed, which will cause it to go to the next line on the screen. So that's how you get the output effect of a new line on the screen. Otherwise, it would write on the same place on the screen. Each time I transmit a single byte, I'm using this code here. And if you remember what I said earlier about the transmit flag, because we have to wait till transmit is complete before we actually before we can transmit another byte. This bit of code here, which I won't explain the C syntax to you, that's quite advanced. Just obviously in my code, just use it as it is, or when you're really strong C programmers, you can start to understand all this symbolism here. But basically, this is checking if the transmit buffer has become clear. It's using that flag in the and this is not actually using the transmit buffer. This is actually using the data register empty flag. There's two flags next to one another in that buffer, in that register. It's using that. It's basically saying when you finish one transmission, you can do the next transmission. And then by writing this data into that register, it will automatically transmit it. So that's all we have to do for transmit. This is quite complex, but this is very simple. And then this is the banner, which is displayed at the beginning. So it just displays some stars and then some text and then some stars. And the prompt is this enter command text. So you can see, if I just now go back to running the code, so the hyperterminal, this is the hyperterminal running on the PC. I've already set it up and run it. And you see that if I enter a 1, the Atmel is sending back command 1 received, enter command. If I send 5, it won't understand that. 5 wasn't in that. It doesn't understand what 5 is. So it just says, oh, I've got some, it doesn't matter. Every time it gets a character, it sends a prompt. So if I can send a G or a Z, it doesn't understand them. But 1 it understands, it gets that. 2 it understands, 3 it understands, and 4. Now, of course, you in your code, this is the actual code now, rather than showing the slides. In your actual code, you can change this. So case, instead of 1, you can make that, if it's a S, stop the motor. If it's a maybe a H, turn the heating on. You can change what these characters are. And of course, then you have a very simple communication system, and you can make it as complicated as you want. And you can add more. Okay, this is just a simple example. So this is not explicitly part of today's lab, but I would suggest you do spend some time studying this particular program and the serial communication, because you will be able to use it in a lot of ways once you understand it, including in your coursework, including diagnostics in your coursework. But also it's a lot of fun because you're actually now, communicating from the Atmel to the PC. And if it was like home automation or something, you can imagine this could be actually not on your PC, this could be on your phone. And you could have a little wireless communication on the Atmel end, little module you can buy, attach that to the Atmel, and you could actually be talking from your phone to your heating system, so that you see you have all the ingredients here to make a much bigger, more interesting system. So I suggest you spend some time studying this, because this is the first step in connecting something and using serial communication. Unfortunately, I can't dwell on this because we have other communication I want to mention in today's lecture. So I'm going to move on. Is there any questions on the user side of things before I move on to other forms of communication?
No, there's no questions.
Okay. Well, please take seriously what I said about having a look at that code. As I say, it does open up a lot of doors. Once you can do this, once you can get basic serial communication working from the Atmel, that opens up a lot of doors, including, as I said, interfacing to various sensors, but also diagnostics on the PC, or connecting to the PC as part of your actual application. So there's a lot of doors open up if you spend a little bit of time. This program is not particularly complex. Ignore the, just copy and use the bits that are complicated, such as this bit and this bit. You don't need to actually understand every single line, but you do need to obviously understand what's going on in the receive loop, because that's clearly where you would modify it. Okay, so I'm going to move on.
Richard, are you going to talk? You mentioned ASCII before.
Yep.
For the data that's being sent.
Yep.
Are you going to explain that a bit more, or later, or?
Well, I was going to move on to the other forms of communication now, because otherwise we're going to overrun so badly.
Okay.
And I think people, what I would recommend is that students spend something like 1 hour at least, in addition to today's labs, to study this code, because it really is a valuable thing to understand and explore it, and not to worry too much about other configurations initially, because once you get the basics working, you can learn the incremental extra bits you need to know as you progress.
Yeah.
Okay.
I just want to say that some students were confused about the data that's coming in, like it's a character, right? And then sometimes you need to have a look at the ASCII table to see.
Yeah, I'm going to talk about the ASCII table at the very end when we talk about today's lab.
Great.
So I'm going to mention that at the end, yes. And everyone needs to understand ASCII regardless of this course. If you're studying computer science or engineering of any kind, you need to know ASCII because it will come up at some point, and we'll be mentioning it today. If you don't already know it, you will need to learn ASCII. Just generally, if you're in computing, you need to know that. So we'll do it later. Yeah. Okay. So let's move on because I'm very conscious that this always takes longer than expected. As I say, I do like to explain things, but it sometimes costs us in terms of the time it takes. So this is the second part of the lecture, and I'll try and cover this quite quickly, but obviously there's a limit to how fast I can go. So we will no doubt overrun again with the lecture, but it's important to cover these different forms of communication. So the Atmel has got not just the COM ports, it's got the serial peripheral interface, and it's got this thing called I2C, which is actually in Atmel's implementation, and in the manual they call it TWI. That's because of a complicated legal situation many years ago where they weren't allowed to call it I2C, but it is fully compatible with I2C, which is an industry standard, by the way. So it's important that it does work with that. And I know from personal experience, it works perfectly well with I2C devices. Okay, so let's be quick but clear with this part of the lecture. I won't dwell on all the detail because it's all in the manual. And if you actually want to connect via SPI or TWI, you will need to look at my sample code in the first instance, because there's a lot of detail that even if I did spend 2 or 3 hours on these slides, we still wouldn't cover every bit of detail. What is important is you understand the basic idea of how they work and have some notion of when to use them and what they can be used for. And I think if I can get that across, that's really important. They're not just there in the background, they actually do get used, and they are powerful when you take the effort to learn how to use them. So we start with serial peripheral interface, and it is designed to be for connecting peripheral devices to microcontrollers or to microprocessors. So it's specifically designed, look at the name of it, serial peripheral interface. This is a communication system that is much more modern than simply USARTs and is designed specifically for connecting these kind of devices together. Okay, microcontroller to microcontroller or microcontroller to peripheral device. It's a 3-wire synchronous system. It's got a master-slave architecture, which means one end is controlling and the other end is just following the rules, if you like. One end is configuring and controlling the clock in particular. Okay. It's designed for one-to-one communication. However, we can do some tricks, which I've done in some applications I've built, where one master can be connected to several slave devices via some extra communication wiring, but that's outside of the standard protocol. So essentially it's one-to-one as far as you'll probably use it. Okay, so some things like an RFID reader, for example, is a classic kind of situation where an LCD, some LCD displays, which like you might be using one today that's got an SPI interface. Some LCD displays and some RFID readers operate with an SPI interface. And the idea is that the device that's going to be controlling communication will be the master side. Okay. You can transmit from the slave to the master, but the master is actually, rather than the slave pushing that, the master is pulling it. So think of it, rather than using these words, maybe you think of controller and follower. If you think of it like that, the controller is the end that actually is in control. And this means SPI is not suitable in situations where data transfers maybe need to be initiated by both sides. So, for example, if you're using, there's a good example here with RFID. If RFID is going to be used with SPI, the RFID reader must be the master side, because the microcontroller does not know when you're going to scan an RFID tag. So the microcontroller cannot ask for the data because it doesn't know you've done a swipe. Only the RFID reader knows that a tag has been swiped or detected. So the RFID reader has to start the communication. So if you have an RFID reader with SPI, it must be the master side that is on the RFID. Okay. If you're using an LCD with SPI, the master side must be the Atmel, because the Atmel is going to send data to the LCD. It's not, it's got to be that the Atmel's got to be doing the controlling. So you have to think carefully about the design. And normally the manufacturers of a module such as an LCD or an RFID will have already, obviously will have understood this and will have devised the thing accordingly. Again, we look at the manual, we see the block diagram, we see quite a lot of complexity, but if we break it down, just like with everything else, everything has a reason and the complexity is not actually as bad as you first think. So first of all, you notice the names MISO, MOSI. You may have seen these when right at the very beginning, when we were connecting the microcontroller to the ISP and the JTAG, and we start to see, you see these wires were used. Okay, so first thing you realize is this is actually used for the programming of the chip in some configurations, okay, because it's a way of getting data into the Atmel. So I won't dwell on that. I'm just flagging it up to you to appreciate these pins here, the same pins. Okay, so this is a very clever system, right? You see the master in, slave out, or the master out, slave in. These are two wires which can go basically from the master to the slave and from the slave to the master. And it's basically, so if you are the master side, this is your input. But if you use the same pin on the slave side, then this is your output. So it depends whether it's input output as to whether this device is the master or the slave. And look at it's like a loop. When we clock, every time we have a clock signal, the master always controls the clock. When we have a clock signal, it controls these buffers. The data comes in here, goes through here, and goes back out there. So if you have 8 bits in your register and you transmit 8 clock cycles, you cause 8 bits to be sent, you'll send the 8 bits from here. But at the same time, 8 bits will also come in from the other side. It's got the various interrupts that we would imagine. So when we receive a byte, you get an interrupt as before, and you've got the various registers as before. I won't go into detail of every single thing. As we've got the clock divider, it looks very much like all the other circuits we've looked at. The USART has its own clock divider called a baud rate register. Here we've got a simpler clock divider, very much like the timers have, but we've still got to control the speed somehow. We've got to have this. And we've got the various configuration setups. This is where we set the main configuration, and this is where we see the status, what is happening. So we've got these various registers and flags, the interrupt request. It's all kind of the same. You get a pattern in the end. All these parts of the Atmel have the same basic operation with control registers and clocks and so on. Now, the master side, I've already mentioned all this, I think, but I'll go through it. It sets the clock speed. If we've got multiple slave devices, then we can choose which one we want to talk to. We can only talk to one at a time, but we can by using different. So let's go back one slide. There is a, sorry, this here, the slave select pin. On the slave side, this has to be pulled low to select the device, to effectively enable the configuration. So if we have 3 or 4 devices connected to one master, we can use a different IO port to control these bits on the slave side to say, okay, so the master can say, I want to turn off this particular slave and turn on that slave, and I can talk to a different one. So, and I'll show you an example where I've done that. So it sets the clock speed, it enables the slave, it provides the clock pulses, and it transmits data in both directions at the same time because of that rotation of the register. And there is another diagram which is coming. Let me just check where that diagram is here. Let me go straight to this diagram because it does explain much better than loads of words. Okay, so if you imagine this dotted line represents one of our devices, and this dotted line here represents the other device here, right? And we have the clock. So if this is the master side, we generate a clock. The other side does not generate a clock. And the clock controls both sides. So we have the clock goes directly here, but also is sent through a wire, which is also part of the programming interface, to the other side. Right now, notice the arrows is really important. It makes a loop. So if I send one clock cycle, one bit will go there, but also one bit will come from here. So if I generate 8 clock cycles, I will transmit 8 bits from here to here, i.e. the whole value of here will end up in here. But at the same time, the whole value of here will end up in here. So in one, if I send 8 clock signals, if I generate 8 clock signals, I've actually transmitted 16 bits, 8 in each direction. They basically cross over because they've got separate wires. That's why these are labeled like this. They can't be called in and out because it depends which end you are. At this end, this is the output, but this is the input. But at this end, this is the input and this is the output. So this naming is very clever. You have to obviously understand what it means. Master in, slave out. All right. And the naming is important because it tells us what is actually happening in terms of the bit transmission. So this is a simple system, really. You put some data in here and you generate some pulses, and it magically appears in there. Well, not obviously magically, but simply it's obviously the 8 bits clock through, and the value is there. So after 8 clocks, you have swapped. What was in here becomes in here, and what was in here becomes in here, and you can both sides can then read those values. Obviously, it's important when we use interrupts with this that we get an interrupt at the end of a whole 8-bit sequence, because it would be really bad if we just sent 2 or 3 clock signals, generate 2 or 3 clock signals. We'd only move 2 or 3 bits. We'd have corruption in here. We'd have 5 bits of the old value and 3 bits of the new value, and the same here. And then if we try to read that, we would have basically rubbish. It would be corrupted value. So obviously the interrupt is only generated when we've had 8 bits have moved. Then we get the interrupt. This is the trick I've done in several builds, where rather than this standard usage, I've managed to do this usage by controlling those slave select bits with separate bits from another port, just using any old port. All we got to do is pull that bit low, and that particular device is enabled, but you've then got to make sure the other ones, the bit goes high, so that you only enable one at a time of these. This is just to show you what I did in a nice simple demonstration. You see the value on the LEDs here. These are some boards I used to use. This is the data pattern on the LEDs. And what was happening here was this master device was transmitting through this cable here, and I had to specially modify this cable with this wire that is missed out of this connector and a crossover here. It's very hard to see, but I had to modify the cable so that each one had a different slave select wire. So this wire does not go to this connector, and this wire crosses over here instead, and the actual wire that was there is ignored. And that enabled me from this end to have the same transmit and receive wires going through, but different slave select wires. And I could basically transmit one pattern to here, and then to here, and then to here. So the pattern here, this is one step ahead because of the camera speed and the fact this is clocking and then updating the data. But basically, this pattern is being sent firstly to here, then to here. And that's a master sending, pushes the count value out. It's just counting and pushing out. And then this is the cable I used. I'll leave you to look at that, because you probably, on a system you build, you wouldn't need that exact cable. You'd use different bits, but well, ignore the cable itself. The actual bit connections would be similar in the sense that not necessarily the port bits, but this labeling would be the same. Okay, you need this. This goes to that on the master. Slave clock goes to both. The MISO on the master goes to the MISO on both slaves. The MOSI on the master goes to the MOSI on both slaves. And this is the clever bit. So use different port bits to control the slave select. And one port bit controls that one, and a different port bit controls that one. That's the only important difference from a standard. So of course, every time you send clock pulses, a set of 8 clock pulses, you get data from the slave to the master, and at the same time data from the master to the slave. So if the master wants to interrogate the slave to say, please can you send me some data, the way you do it is you have to send a code to the slave saying, please get some data and put it in the register, and then later on the master has to do another transmit of 8 bits to get the value. So if you imagine, if we go back to that diagram there, because the master's in control, the slave can't just generate data and send it when it wants. But what can happen is the master can send a special code which the slave reads and says, okay, he wants me to read temperature, for example. So the slave could then read the temperature, put the value in here, and then the master waits a short amount of time and then does another 8-bit rotate and gets the temperature value across. Or if you're going to do it periodically, the slave just keeps reading the temperature value and puts it in here every time. And then the next time the master reads it, it will get the temperature value from the previous value. You know, so you could do this once a second or something like that. So in your design, you do have to synchronize 2 different things going on here. One is that the slave device is creating a value here of data, and that the master is then clocking that data across. And the 2 actions may be independent, right? So, one end may be generating data, put it in that register, but it doesn't control sending it. It doesn't matter as long as the master side is receiving, is causing this process to happen at a suitable speed. Then it's okay. If the slave is reading the temperature and putting it here once per second, and the master is reading this once per second, or even once slightly different speed than that, it will still always get the latest value that is in the register. But you do need to appreciate you would have slightly not perfectly synchronized actions at each side. One would be putting data into here, and the other is reading the data across from here, but not necessarily in perfect step with one another. Okay, but it works fine. And again, it's down to you understanding how this works so that you can design things that use it in a sensible way. We've already seen these slides. I was just going back to that one, wasn't I? And this is the example where the master is pulling data from the slaves. So these switches are built into these boards. And here I'm pushing the one that is equivalent to a 32, my fat finger on a very small button, but that is me pushing a button there. And you see that the master, and here's the LCD as well, which is coincidental, we'll be using that later on today. So the master is sending a value to this slave, first of all, saying read the value, get it back through, through that rotation, and then this one, and then this one, and then this one, and then this one, alternating like that. And it's displaying the result it gets from this one, slave 0, on the first line of the LCD, and this value on the second. Now, if no switches are pushed, you have data value 0. But because I'm pushing that switch there, I'm getting data value 32. And this obviously is constantly updating. As I push the switches here and here, I'm getting these values changing, okay? So you will see in my some of my older sample code, some of these examples, and I've actually, I think last year, I modified them to work on the 2560. So you have some examples of the SPI and also TWI on the 2560. So now we look at I2C. Can I just say for the SPI, I have covered that very quickly. I appreciate that. If anyone's actually using it and they get stuck, start by looking at my lecture slides. look at my sample code, look at the manual, and then contact me directly if you have particular concerns about how it works. You want more details, because it is something we could talk about for hours and hours and go into great detail, but a lot of you won't even be using it. So it seems a waste of resources to do that. But I have provided sample code. There are slides I've just gone through, and there is also the manual, which goes into great detail of how it works. So use those resources. The sample code really is the best place to look, and then come back and ask me specifically if you have a question. I may be able to provide more information if it's a very specific question about those things as well. All right, so I'm going to move on and talk about yet another type of communication, which is I²C, which is very, very important that we cover this one as well. And it's obviously nice to be able to contrast I²C with SPI, because they are quite different. It's a nice pair to contrast against one another. Okay, so let's have a look at this now. So this is again specifically designed to connect microcontrollers on the same circuit board, i.e. designed to be very short distance, very flexible. Now, the distance thing is not such a problem if you go slow with it, but if you run it at high speed, the distance becomes quite critical, because it's tricky with capacitance, the way this works. So the idea is the original system was 100 kilobits per second, which was fast for communication in the 1980s. And now the mode we'll be using in my sample codes and the mode that I would use generally speaking is 400 kilobits per second. But we can make this work at 3.4 megabits per second if we have devices running fast enough speed to need that. But this is quite fast for most data for sensors. This is, even that is very fast to configure sensors. This only uses 2 wires instead of 3. So whereas the SPI was a 3-wire system, this is a 2-wire system, and this is a bus. It's not a one-to-one system. This is a one-to-many or many-to-one system, and therefore devices need addresses. So we're now essentially a kind of networking where each device has its own address, and the master, any device can become master. That's another thing that can happen. The one that is master at any particular time can talk to whichever other device it wants to. So the main features we need to know are it's a 2-wire system and it's asynchronous, which means the clocking is done only when we need to do clocking. There is a separate clock line, but the clock is not running all the time. Okay, so it's considered asynchronous in that regard. It's a wired AND architecture, which means that there will be a diagram coming up to show you that, but it basically means the lines are left to float high with some pull-up resistors, and only so imagine that's a high level, and when we transmit, we pull them low and then we release. So that if the line's high, it means nothing is happening, and when data is on the line, it goes low. And so if someone is doing nothing and someone else is transmitting, then the one that's transmitting will win the argument, if you like, a 0 and a 1, because the 1 is the 0 is pulled low by a transistor in the device, and the 1 is just a pull-up resistor that will just pull it there by default. When you see a diagram, it will become clearer. But wired AND means that if one device is transmitting a 0 and one device is transmitting a 1 at the same time, the 0 will win, okay, because it's been pulled low with more power, if you like, than the 1 has. I'll explain that with a diagram. The master-slave roles are dynamic. You can divide, it's simpler, and you can design things where the master is pre-selected and the configuration is simpler. But you can also design a system where any device can become the master and transmit some data and then stop being the master. And that works really good in a kind of sensor network type application. We have a 7-bit slave address, which means we can have up to 128 devices altogether. Okay, but bearing in mind that if we are having dynamic master slave roles, every device is by default a slave and only becomes master temporary, right? So in fact, that means the 128 is the total number of devices. But if we have a fixed master, we can actually have 129 devices, because then you can have one master and 128 slaves. Okay, but then you can't have the dynamic master slave roles. We can also do broadcast with this, which is really powerful. Now, the idea here is that you send one data value and it goes to every, you could have literally a whole load of sensors, like a lighting. Imagine doing stage lighting at a theatre or something, where you have massive displays of lights. You want to control what's going on. And this is along the lines of real applications in stage work and lighting design and so on. You can imagine your devices all controlling different lights on the stage, and you can actually control them with patterns that are synchronizing them all. And sometimes you want them all on, them all off, or all the red ones on, all the blue ones on, and stuff like that. And this broadcast can be very powerful. That's just one application, of course, but I've seen a student at Greenwich who did an application like that in a project, and it was very, very powerful. He actually was studying stage technologies, so that was he was interested in that, and very, very interesting use of this. Any node can grab the bus and become the master. This is in the dynamic roles concept, but the downside is using this is more complex, and I'd say far more complex than SPI. Okay, so again, you need to look at the manual by sample code, etc. I'm going to try and now show you through the basic usage of this. And the same applies, I think, I'll just say at the beginning rather than the end, the same applies that if anyone actually wants to use this for real in this course, then you need to start with these slides. Then you need to look at the sample code, which is where your main, because you're going to see working examples and go through that code. Then you're going to need the manual to reinforce that, and then come to me directly and see if I can add something and help. But obviously it's difficult to remotely diagnose things and so on, but at least I will be able to hopefully give you more details on how to do it. Because as I say, if I was to try and explain everything about this communication system, we would be here for the whole day. And even then, maybe I wouldn't be able to explain everything. And of course, some of you will never actually use this in this course, so it would be a waste of resource in that regard. But I will do my best to explain the overall usage, because it's a very powerful system, and it's like when it's in your toolbox, you know it exists, you know how to use it, you know what it can do. Then you have the option to use it when it's appropriate, and the option to avoid using it when it's too complex and you don't need that complexity, and you can get away with something simpler. Because the rule should be, if you can use a simpler communication system, you should. The TWI, also I2C, the other name of it, is complex, and I would not suggest you ever use it if there's another simpler way to do it. Like, I wouldn't use it in place of a USART, simple serial connection, because it's so much more complicated. The fault finding, the debugging is worse. However, if you want a broadcast system, or a system where you've got one device talking to 127 other devices up to that number, then this is ideal. And you cannot do that with USARTs, and you cannot do that with SPI, not easily anyway. It's very complicated. So this is the way to connect multiple devices. Okay, it's not really suitable for one-to-one communication because of the extra complexity you have to go with this. This is also used in terms of applications similar to SPI. I've used this to connect Atmel to Atmel, and I've connected 5 different Atmels together using this in one application. I've used it to connect RFID readers, LCDs, so the same kind of devices that you might use with SPI. And of the two schemes, SPI is simpler. So as I say, let's go through some of the applications and some of the usages. Here's a scenario where you can imagine the kind of jobs you might be going into in the future. You might be you're going to be engineers with embedded systems knowledge. So the kind of thing you might find yourself working on could be a system where there's lots of devices somehow synchronizing. maybe an automated factory, or maybe these are all parts of a car with different controllers in the car. But here we have illustrated of several robots and conveyor belts, and you can imagine this robot is putting something on a conveyor belt, this one is picking it off the conveyor belt, doing something, putting it back on the conveyor belt. So you have all these different controllers, and you need to have some kind of coordination. So this would be an example of where the two-wire interface bus would allow these devices to all talk to one another and be coordinated, or maybe not have a coordination. Maybe they just all become master when they want to, and you don't actually have to have this. But in reality, you'd probably have it done this way. So it's kind of a centralized control. Okay, so each of these can have their own sensors and their own actuators. And essentially, rather than trying to use one microcontroller to connect all of these sensors and actuators together, what you're essentially doing is making the problem more modular, have lots of different controllers doing different little bits of the job, and then somehow get them to share the work and communicate. And the communicate becomes the part we're really interested in today. So the TWI master generates the clock and initiates transmission. It can either push data or pull data, i.e. ask the other end to send data, or it can send data itself. The slave can either respond, well, can only respond to the master request. It can either read or write data from the master, and it can wake up from a sleep mode, which is a thing that the Atmel provides these modes of really low power where you can shut down the CPU, and you can actually use a two-wire interface signal to wake up the device from sleep. So when it's to save power, it can be sleeping and then wakes up and does something. Yeah, and as I said before, we can swap which one is the master, but that is managing that is reasonably complex. So we probably won't do that in unless we really have to in an application. So the concept is you have this bus. So it's not one-to-one, as I said, it's one-to-many or many-to-one. This master can talk to this slave or this one using the 7-bit address, which identifies each separate slave. That's the master is fixed mode. This is the where masters are dynamic. So by default, everyone is a slave, and then one can be a master when it needs to be. And the diagram then temporarily looks like this, but goes back to looking like this again afterwards. Okay, so every device has to have the same code here, and every device has to have the ability to operate as the master. Whereas here, the master has to have slightly more complex code, and these only have to have the slave side of the code embedded in them, because they will never be a master. So again, if you are using this, which itself is complex, then this is a less complex way of doing it. This is more complex, but this is full power, like almost the same power as a full computer network. You can do pretty much anything you can do with a full computer network with this. Okay. Again, I'm going to just go over the electrical side of it quite briefly, because I know certainly for this particular course, we're not interested in electronic engineering so much, but some of you are engineers who will understand this or will want to read more about this. The speed and length of wire relationship is critical with two-wire interface. The cables we use, I use Cat5 in my implementations. If you're just using ribbon cable, you can only have very short distances, but ribbon cable has capacitance of about 46 picofarads per meter, and Cat5 cable has capacitance of approximately 50 picofarad per meter at this particular speed. Now, the reason I say that is because I've used this myself at 97 meter distance. Given that this is intended to work in centimeter distances, I've slowed this right down, used Cat5, RJ45, and used it over 97 meters. It's intended to work over 5 to 10 centimeters on the same circuit board at higher speeds. I've slowed it right down. And the trick is to understand the relationship between the capacitance and the frequency you're using it and the length of wire. And again, it gets very technical and lots of experimentation. There are hobbyists who have their home automation and 12-volt power systems. Most of them are in America. And there's a whole group of these hobbyists who, have solar panels, and they run their whole place on their homemade solar panels and their wind generators and that. These tend to be small wind turbines down the bottom of the garden on a post, and so on. And there's a whole community of these people. And some of these people are using this because it's low power, low cost, and they're controlling these things with 1 kilometer ranges. This designed to work at a few centimeters. But remember, by doing what they're doing to achieve that is slowing down the clock right a lot. So the rule you have to follow is that any cable has reasonably high capacitance, and you have to make sure the capacitance does not exceed 400 picofarad on the whole bus, and regardless of how long it is or how many devices are connected. Okay. The speed I used to get this distance, I had to go down to 38 kilobits per second, which was absolutely fine for simple sensor control. This is the system I use just to show you what I did here. I also did, you've heard of power over Ethernet, I expect. Well, I invented my own power over TWI. So I had a single Ethernet cable with the power line and the TWI going over this. This was 97 meters long. These two are on the one end with the power supply, and these three were a long way away. And there's a drum of cable in between here connecting these together. And actually, these were tested down. They were physically about 30 meters away, but the cable is much longer. It was on a roll for test purposes. Okay. And then I was obviously in the study, when I took the photo, I had to bring them all onto one table, and these boards have got electronic circuits on the back, so that's why they're on paper and so on. But basically, I had to build these are home built, and these are just some of the things you can do once you understand how this works. This is quite a fascinating little project. My own little line drivers to drive the bus, but this is the important thing to realize is normally the distances you would use between two TWI is literally this kind of distance here. This is the normal distance. But if you slow things right down, you can achieve massive distances. And this therefore becomes a very good tool, two-wire interface, to have in your toolbox for really complex. So if you were building something where you have something in your house and something in your garden connected together, maybe some security application or something, this is quite a nice option. Okay, I won't go into great details with this either because it's complex, but you need to have a general understanding of how it works. So I'll keep this at a high level, but I want to make sure you understand the basic idea. You have a data signal and a clock signal, and these are two separate wires, and this is why it's called two-wire interface. Okay, so one wire is your data and one wire is your clock. And the device that is transmitting is automatically labeled as the master. That's really what all that is happening. The one that is transmitting is in control. And the one that is receiving data is basically just following what the controller is doing. And when the clock signal is high and the data signal goes low, that combination means transmission is about to begin. This is that I want to transmit signal, and then the clock signal is continuous. So I've obviously this actual diagram is from the manual, but you can imagine that there would be lots of clock pulses. This is just a cutoff, and you would transmit your data. And when the device that's transmitting can choose when it wants to stop transmitting. So to stop transmitting, the data line goes high while the clock signal is high. That is a signal to say stop transmitting. Now, to stop multiple nodes all transmitting at the same time, they have to watch out for these signals, and obviously follow the rules. And once this signal has been cleared and everyone has seen the stop signal, then another device can start transmitting. Okay, so basically it comes down to looking at these two lines and looking at the combination of values. Normally, the data can only change values when the clock is low. So when the clock is high and the data changes, that's how we know it's a start or stop signal. Okay. When the other changes all occur when the clock signal is low. And this is how the clock also works, because you know that is a data signal because the clock is low. Remember we said earlier, the clock signal goes either high or low to signify data is changing. It's a new data value. So every time a new data value occurs, the clock will go low, and then that will be either a 1 or a 0. That will be either a 1 or a 0. That is the actual data because the clock is low. When the clock is high and something happens on the data line, that's how we know start or stop is occurring. And here we have a situation where a device transmits some data, start, and then maybe it sends to one particular device. Then it wants to send to a different device. The same device wants to keep sending, but maybe to a different device. So it starts and it says which slave it wants to talk to, as the address is part of the data that comes after that start signal. And then it can start again and send data to a different device before it stops. So this stops, this basically hogs the bus and stops another device starting to transmit, because this device wants to talk to maybe device C wants to talk to D, and then C wants to talk to E immediately afterwards. It doesn't want another device to start talking. So it keeps hold of the bus. So instead of sending a stop, it sends another start. Okay, so this is quite a powerful protocol, but the design has to be carefully considered when you use this. You can't just throw this together like with UseArt. You can do UseArt configuration in 10 minutes. This takes probably 2 days to plan and check and test everything. It's quite a complicated protocol to use, and you have to be very careful. But when you do use it, it's incredibly powerful, incredibly flexible. So the overview, notice this is only in a block diagram. We don't show the individual connections of everything because it's just too complex. Okay, this is your clock, and this is your data. Look at the this is the clock line and the data. Okay, the slew rate control and the spike filter is just really adjusting. If we go back, I'll show you what I mean by those things. Slew rate is the angle of this, how fast these things change. And spikes are obviously pulses that are very short, that little spikes that would mess up the communication. So this is just electronic filtering to protect the signal and to clean up the signal, get rid of noise. So you don't, from a programmer point of view, you don't have to worry about this at all. Engineers are interested in this. Programmers are not interested in this part. But you see the bus interface is complex. You've got your start stop signals, and you're using your data shift to actually get the address or the data into your data register, because the first thing you send when you transmit is the address of the other device you want to talk to. So if device A wants to talk to device B, the first thing device A has to do is send the address B, because the other devices listening need to ignore this signal because you're talking to device B. You're not talking to device G, H, I, etc. So we have to have some extra logic to control sending the data and sending the address and working out if it's our address or not when we're receiving, because when we receive data, we need to look at, is it our address or someone else's address? And if it's someone else's address, we ignore it. So that is also, adds some complexity here. And then we've got the same problem we had with the UseArt and the TWI, the SPI. We've always got the clock speed to consider and the pre-scaler. There's all that complexity as well. This is the actual address match. Is it our address or not when we receive an address? Check that. And this is the general control unit with the status register and the control register that we program values in these, and we read flags, etc. from here. Okay. This is quite a complex protocol, so it has a state machine to control the overall behavior. And if you are going to use this, you need to study the state machine at least a little bit to understand it. And I'll show you what I mean in some later slides that will come after this. In terms of connecting things, it's very simple. you just connect all the data signal together to every device, your Atmel and all your sensors, and maybe there are 2 Atmels, 3 Atmels, and 10 sensors. By the way, this is an interesting idea, right? Supposing you've got 1 temperature sensor and 3 Atmels, you could do this. You could use this so that 1 temperature sensor is connected to multiple Atmels, because normally you would think, oh, well, I might have 1 Atmel with 3 temperature sensors, but you might also have 1 temperature sensor with 3 Atmels with this, if you're careful how you configure it. So this could be a mixture of Atmels, other microcontrollers. It could be some Atmels and some other manufacturers' devices, and some temperature sensors and all kinds of things all connected on this bus. And the way this works is that these bus lines must be high when no one is transmitting. That's how it works. That's what we mean by this wired AND. So when someone transmits, it pulls the value low. So these are high by default. So we have to have these pull-up resistors so that when nothing is happening, these lines are always high, 5 volts typically. And to explain how that wired AND works, because it is quite important, if you are going to use this, you would need to understand that. The reason it's called wired AND is because with wired AND, 0 is actually more powerful than a 1, because if both are doing nothing, they would put a 1 on the bus. And if there's a 1 and a 0, where 1 is doing something and 1 isn't, 1 is writing a value and the other is just leaving it as a 0, sorry, leaving it as a 1, the 0 is going to win, because the pull-up resistor is quite weak. It will pull the line high, but with low current. So if something transmits a 0, it pulls down with strong current through a transistor. That pull-up resistor is only weak. The voltage will go down very, very easily to 0, and the resistor won't be able to overcome it. Obviously, the choice of the value of the resistor is important, and there's notes in the manual as to how you select those values, etc. You must obviously use the right value of resistor. That is important. But so when you write a value such as a 0, you're pulling the value low. That's going to override a 1 where it's just floating high. So the 0 always wins. So this is why we call it wired AND, because only when the truth table is an AND, right? So 0 and 0 is a 0. A 0 and a 1 is a 0. A 1 and a 0 is a 0. And a 1 and a 1 is a, this is AND. 0 and 0 equals 0. 0 and 1 equals 0. 1 and 0 equals 0. 1 and 1 equals 1. So this is why it's called wire AND, because the 2 systems transmitting will give the output of these. If one transmits a 0, one transmits a 1 at the same time, the result will be a 0. And so we actually get, the effect is a truth table of AND. And it's important because suppose 2 devices are transmitting at the same time, which they shouldn't be if you've designed everything correctly, but they could be. Now, 2 devices transmit at the same time. Node 1 is transmitting all 0s, it's pulling down low. And node 2 is transmitting a value such as 0, 0, 1, 0. Well, because this value will win over this, the end, what will actually go on the bus will be this. These will always win over a 1. If this happens at the same time, this one will win. And therefore, on the bus, you will see this. And node 1 will see that it transmitted that pattern, and that pattern was on the bus. So node 1 is happy. But node 2 will see that it transmitted this value, and it actually on the bus was this value. Right? It will see that. It will see that it transmitted, the 1 was ignored. So it knows it has lost arbitration. It knows that something else is on the bus as well. And node 2 will stop transmitting. And node 1 has now control of the bus. And once node 2 has stopped transmitting, it must not start transmitting again until it sees a stop signal. So this is a way in which if multiple transmissions do occur, one device will win effectively. It is like automatic voting, really. The first one to transmit a 1 when the other transmits a 0 loses. And if they're both transmitting at the same time, the same value, by the way, there's no data loss. Because here we had 2 signals on the bus, and the node that won, its data was not corrupted. The one that lost arbitration, its data was corrupted on the bus. Its signal was lost essentially, but it doesn't matter, because once it realizes it's lost arbitration, when it does eventually start later on, there will be a time in the future where this one stops transmitting. This one will see a stop signal, so it can now start transmitting, and of course it will start its data again. So the data is not really lost, it's just delayed. Okay, that will transmit its data later on. In terms of transmit and receive, if we want the master to be the transmitter, then of course that's going to connect to a slave being a receiver. And if we want the master to be a receiver, then that's going to obviously connect to a slave being a transmitter. And we have these special codes. So basically, in order to transmit, you need to send, first of all, you need the start bit, which is done with electronics, that causes the data line to go low while the clock is high. So that's first. Then you need the slave address, and then you need a special bit on the end, which is the write bit, which basically tells the slave, I'm writing to you. Because otherwise the slave doesn't know, are you sending me data or do you want me to send you data? So this is a single bit. So this is 7-bit address. See, why is it 7-bit address? Well, here's one reason. You need this other 1 bit to tell it if it's read or write. This is a 0 is your write, and a 1 is a read. So if I send it 7 bits of address plus a 0 on the end, it means I'm going to send data to you. But if I send its 7-bit address plus a 1 on the end, it means I want you to send me data, right? So this is how we do it. So this is obviously adds up to 8 bits. So this is why, or one reason why, this is a 7-bit address, okay? So now this is where it gets complicated, and I won't try and explain this. I'll just bring it to your attention so you can look in the manual, etc. But basically, in order to transmit, this is the start signal I've mentioned with the electronics does this. This is our slave address plus the W. This is for if I want to send data to the slave, I'm writing. Then we leave a gap where the slave can send a 0 to acknowledge. So the slave, after I've sent, I leave a 1-bit gap where so the master leaves the wire. Let's go back to that diagram of the wire. The master will leave the wire at a high. Oh, sorry, that's not so, that's a better diagram. The master will leave the wire high on purpose, and the slave will send a 0 to say, I understand, I received that message. So the master purposely leaves the signal high for 1 bit and sees if the slave sends a low, like that. And that's what is happening here. And if the slave sends a low there, it means it understood that and it is ready to receive data. And then the master can send the data. If the slave did not respond, then we call that a NAC. So this an ACK is an acknowledgement, and a negative acknowledgement or a lack of an acknowledgement is symbolized as a not ACK, also known as a NAC. So an ACK and a NAC. These are real terms in communication, by the way. I'm not making up them, okay, in case you think I'm talking mad when I start talking about NACs and ACKs. These are actual terms. And a NAC means, and there's 2 types of NAC, actually. There's a NAC, which is basically a missing ACK, where there is no acknowledgement. But there's also, in some systems, there's an explicit signal called a NAC, where you actually purposely send a message that says, I didn't get it. I received an error, send it again. So sometimes a NAC is implicit, like here. Not doing anything means it's a NAC. But in some systems, sending a special code that says, I received an error, can you send again, is an explicit form of NAK. So there's multiple ways of doing that. But an ACK is a common idea that basically what happens is the master sends, I want to talk to slave number one, I want to write to slave number one. Slave number one sends it, puts a low here, which says, I received that, I understand that, okay. Then the master can send the data, the slave can read that and say, yes, can set that, so yes, I received that byte. And of course, you have many bytes of data. And then at the end of everything, the master says, okay, that's the end of my data. It sends a stop signal, which is hardware only. So the data line goes high while the clock line is already high. And that's how we stop the transmission. Okay, so this is the protocol on the line. And you can see that's just one scenario. So you can see all the different how we send a start condition. We have to program one of the registers in a very particular way. I won't go into all the complexity of this. As I said, if you want to use this, read these next few slides carefully. This is the actual, maybe we'll just go through one scenario because there's 4 scenarios altogether. Master sends to slave, master receives from slave. Because of the master slave combination of which one's which, there's actually 4 ways 4 different scenarios that can arise. If we just look at what happens here, just in one sequence, going from the master to the slave, if you imagine this is the master, this is the slave here. So the other devices are doing nothing, right? And here's the pull-up resistors. So in order to make this work, so the master is transmitting data to the slave. First of all, the master will set the start condition and then send the slave address and the write flag so that the slave knows it's talking to, so slave address of this device is what is being sent there. This slave knows that the master wants to send data to it. So it then sends the acknowledgement. So the acknowledgement is going from here to here, essentially, although it's on the bus. So they all the devices could see this signal, but only these 2 are interested. Then this sends the data across. This says, okay, I got that. So it sends the acknowledge again. And this can happen many times. And at the end, the master says, okay, that's it. I don't want to send anymore. So it sends a stop signal. And this stop signal, noted there's a P here, and the start signal noted as an S there. These are hardware only, automatically done by setting these flags in one of the registers. I won't, as I say, I won't go into the depths of that. There's a lot of detail here. These are essentially parts of the state machine. And again, I will just highlight the fact it exists for you. I won't try to explain how it works in detail, but we already saw this kind of notation: send the start bit, then the slave address, then write flag, then the slave acknowledges, then data. This is the same bit again, but in each case, things can happen. So what if you didn't get an acknowledgement? What happens? Okay, what if you get the data gets sent, and instead of it being acknowledged, like in the scenario we just looked at, what if it's not acknowledged? So then the master's going to stop, right? In each case here, the master, if you don't get an acknowledgement, it's going to stop. So this is trying to show essentially a kind of state machine representation. But unfortunately, these diagrams, if we look at the different scenarios, these diagrams get more and more complex. And so, yeah, you've got lots of different scenarios, and I'm not going to try and explain all them to you. Please start by looking at my sample code for this if you do choose to use this. And hopefully you'd be able to get my sample code to work with a few modifications and not necessarily have to write code for all of this yourself. And I've written the kind of library support for this, where most of it is dealt with in the sample code, and you can just modify it slightly without having to personally write all this stuff. But you can see just by these couple of slides here that the state machine of what goes on in this protocol is complex, and you wouldn't use this by first choice if you could just use a useart, for example. And in fact, if anything, this reinforces how useful the useart is, because it's so simple compared with this. But if you want to do something interesting and complex where you have multiple devices effectively networking, then you need this and not the useart. So what I've done today really is go from the simplest to the most complex communication all in one session, really. And hopefully now you have these ideas of what is possible, what the different modes of communication are, and which one is best in a certain situation. Okay, that's hopefully what we've achieved there. Now we're going to go quickly look at the lab. So are there any questions at this point on the 2-wire interface?
Nope.
Okay, so I'm going to very quickly cover today's lab, and I will be as quick as I can, but I obviously I'd rather make sure I cover it properly rather than rush. So I'll be another 10 minutes or so. Sorry about the overload. At least you're getting quality. At least you're getting value for money. I'm not. At least you're not getting short lectures. But the downside is you get hungry. Now, this is a supplementary lecture, but this is really only here to support the lab. Okay. So I've made an assumption that your kit has got an LCD in it. Is that true?
Yeah.
Brilliant. That is good, because I did expect it would have. And if not, you can get these now for just a few dollars. So it would be always worth buying one if you didn't have one anyway. So I think it's fair to say that the liquid crystal display is in almost every microcontroller application. Very, very large numbers of them have these displays, and they're so much better than LEDs for actual information. So again, you have to make choices of what is the appropriate way to display data, right? Sometimes an LED that is on or just flashing or flashing at high speed, low speed, one LED you can do a lot. Two different LED colors, you can do a lot of information with just 2 LEDs. You can have one flashing, one on, the other flashing, both just on, one flashing fast, one flashing. So you can do so many data signals with just 2 LEDs. Even 3 or 4, you can do massive things. But eventually, if you want to start being user friendly, you start having to have some text, tell the user what to do, or tell them what kind of error has occurred or something like this. So you end up needing LCDs for more interesting applications in the end, certainly for more user-friendly applications. There's loads of different LCDs. Basically, the difference is in terms of how many characters you can fit on each line and how many lines you have. That's the basic difference from a programmer viewpoint. From a user viewpoint, they look different. Some are prettier than others. Some have got better fonts and things like that. But from a programmer viewpoint, all you really need to know is how many lines and how many columns, how many rows, sorry, how many lines, how many lines, how many columns, how many characters can you fit? That's all you need to really know. Most of these LCD modules have an embedded microcontroller built into them. So you're communicating to them via a USAR or via SPI or possibly even TWI in some cases, but normally it will be a USAR or TWI, or it may be parallel communication if it's short, like the one that I use. Because it's only short jumper wires distance from the microcontroller, I'm using it parallel. I've got 8 data wires and some control wires connecting to a port on the microcontroller. And in today's sample code, that is the way I'm assuming it. I'm hoping you have an LCD that is capable of that.
Yeah, we have. Yeah.
Brilliant. Again, because they do sometimes change these kits and it would mess things up a bit. Okay. So the data connections, again, this is the sample code you'll be using today in the lab. And this is the sample code that I'm basing this slide on. So I'm using port A for my data. And on the mega board, it's got these pin numbers, right? So you can find that. And this is the data on the LCD module. So you need to obviously wire the LCD up to that. And I'm also using port G for control, which has got port G bits 0, 1, and 2. And G0 is register selects because the LCD has registers in there that allow you to control things like whether you want it to auto scroll, whether you want the cursor turned on and off, and where you want to position the cursor, things like that. So we have some control we have to do. And we need to also have a read or write control bit, because when we're sending data, we're going to be writing but we may need to read control bits or something from a register. So we might occasionally want to read from the LCD to see the configuration. And we have an enable as well. And then we also have some extra wiring for the power supply and a variable resistor, which is also in your kit, or it used to always be, with 10 kilo ohms, or, well, that works okay. A higher value will also work fine. And you will basically connect your LCD, your variable resistor will have one wire connected to that, the other to that, and the mid wire going to V0. And this is just basically a contrast control. If you don't have a variable resistor, you can just have two resistors, so 10k from 5 volts to this pin and another 10k from 0 volts to this pin, and then your brightness of your LED LCD will be about in the middle, hopefully. Some LCDs, this is the actual font brightness. Some LCDs also have a backlight which you can turn on. This is like basically an LED built into it. So anode and cathode, A and K, are the LED. Sometimes you see an LCD display with a nice blue light in the background or something like this. And this is something we can turn on with extra wires. You don't really need that for today's lab, as long as you can read the text, as long as the contrast of the actual text is suitable, that's okay. Now, this is a picture of the kind of LCD that I'm expecting your kit to have. And some of them have already the wires soldered in here, so you can plug this in directly to your breadboard. And some of them you have to get the wires soldered on. Stephen, which type have they got?
Almost everyone has to solder on.
Oh, it's already on. Brilliant. That's even better because you don't have to worry about that. And there's your anode and your cathode for your backlight. And then you have all these data lines, and you need to follow the various tables in this slide and the previous slide to connect everything, okay? The logic diagram is basically, here's my, this is all part of the LCD. So my Atmel is over here. It's got data, it's sort of the read, write, control, the enable, and the register select coming in. And this is going into here and into here, and various control. And your backlight control is basically turned on or off. And your variable resistor is wired across the supply, the middle part going to that V0 signal, which allows the brightness of the black writing on here, the font itself is controlled by this. You do not need the backlight for today's lab, or you should not need that. But if you don't have this connected, you might find you have no text. You might find if you disconnect this, it's automatically on full, nice, very dark writing, in which case you don't need this. So try it. It might automatically, by default, the lack of this might set this as a nice dark writing. But if you have no writing appearing on your LCD at all, it could just be this value is wrong. And it may be that your program is correct. Okay, so use my sample code to start with, and you should have text appearing. And if it doesn't appear, then, as I say, check the brightness control first, the contrast control first, before you start wondering what else is wrong.
Or the wiring.
Or the wiring. Well, yeah, here is a picture of my one that I use. Okay, so it's on my breadboard, which is screwed to the board so it can't move. So here is the wiring. These, what I've done to simplify things on my one, I've used the data is these 4 yellow and these 4 other ones here. There's data 0 to data 7, and these all go to port A, which is over there on the end. Okay. And then the other ones, the read, write, these other 3 on the end here are going to the enable, the read, write, and the other control line are going off to port G. The wires are over there somewhere as well. And there's my variable resistor. And you see the middle of the variable resistor is going to the V0 pin. So I can turn this dial here. I've got the ends of it. One is going to the 5 volt. One is going to the 0 volts. So I can turn the dial and change the brightness of the text on here. Okay. And the backlight is controlled. There's the anode and cathode. So the backlight is controlled with a resistor which to the anode. So it's going from the 5 volts through a resistor to the anode, and then from 0 volts to the cathode. So that is just fixing the backlight on all the time in my one. Okay, that's the actual wiring. So although you may not lay out your breadboard exactly the same, it gives you a kind of clue as to what I've done, and you can see some of it clearly. But you've also got the diagram on the previous slide. Here's another picture from a different angle, showing what's going on. So here's port G, here's my control signals, here's port A, my data signals, and here's the 1 kilo ohm resistor for the backlight. Okay, there. So you can see a bit more from this diagram. There's my variable resistor again, behind all the wires. All right, so you see quite a lot from these 2 diagrams, plus the so these 2 photographs, plus you've got the other circuit diagrams on the other slide, and you've then got this information as well, which is summarizing it from the program point of view, but it's obviously the same information, port G, port A. And port A uses data, but also in certain modes, port A bit 7 is used as control as well. So you have to look at the sample code to see how port A is used as both a busy flag and as data line. Okay, it's just it's done within the sample code, and these are obviously these 3 bits here are how you configure the LCD to do different display settings. And again, you need to look at the sample code, which I'll show you in a moment, to make that clear, because always it's more complicated when you start looking at how it actually works, and the sample code will show you how it works. There's also a library of functions I've pre-written for you, which is called LCD Library Functions 2560.h, which you will see in the sample code is being used. And this does things for you. So in your own code, you do not have to do things like check the LCD if it's busy. Wait, again, it's a serial communication. You send a character to it, you've got to wait till it displays that character before you can send another one to it. It's working slower than your CPU works, basically. You can output a function command to the LCD, clear the display, set the cursor back to the home position, which is the top row leftmost character normally. Set the cursor to any particular position you want. Write a data character to the LCD at that position. And also a rather sort of quirky thing that I did for a particular application a few years back, and I've left it in the library, is to convert your LCD into a 2-bar bar graph. So if you imagine, if we just go back to here, if you imagine sending just square blocks, and you have 2 bar, you could have a 2-bar bar graph that is dynamic, moving with these 2 bars. And you, instead of using letters, you're using, like, imagine from the bottom here, you could have the bars moving up and down like a little mini graph with just 2 bars. And if you had a 4 display, you could have a 4-bar bar graph on here. I just did that for fun a couple of years ago with an accelerometer, moving these 2 bar graphs. But you could use it in a real application. There's no reason why you can't use an LCD as a little bar graph if you want to. And it's just novel. So I'd like to show people, think outside the box. This is a little bit of outside box thinking from me that you might want to use in an application. Okay. This is the ASCII table. Now, the ASCII, there are better presented ASCII tables than this particular one. This is a picture of a manual that I took. There are loads of web resources which got ASCII tables that are slightly better presented than this, but this is specifically for the LCD that we're using, okay, or the one that I'm using, the 1602 model, which is the one that's the actual control module, which is in nearly all of these LCDs. Okay, they nearly all have the same control circuit inside them, and so we can pick out these symbols, and we can pick out, for example, this plus minus symbol, or the letters A, B, C, D, 1, 2, 3, 4. There's an English pound sign there. There's an up arrow, a sort of carriage return symbol. There's loads of characters here. Some little Space Invader type symbols or something. All kinds of things are here. And so to understand the character code, you have this this first byte numbering and the second byte numbering. So if I look at the code A5, 5, A5, I get the pound symbol. This is in hexadecimal, right? So if I look at the code 30 hex, right? 30 is 3 times 16, so that's 48 in decimal. I have the code 0, and 49 in decimal, which is 31 in hex, I have 1, and then 32 in hex, okay, which is 50 in decimal, is the character 2. And you see how these characters are selected based on the code. So you need to have a basic understanding of ASCII, not just for this course. I really think everyone in computing needs to know this. And here is the other half. Now, the standard characters like the A, 1 to 9, A to Z uppercase, and A to Z in lowercase. Some of them are here still. Here's the lowercase characters, and here's some more here. These are standard, whereas some of these graphic symbols are not standard ASCII. Some ASCII systems will use, especially the higher end of the code, these ones here. Some systems will use slightly different characters in place of others, or they'll display differently. It will still look like the same symbol in the table. When you actually display it, you may get something else in some of these places. But the characters in the standard position, certainly the first half of the table, will always be standardized, okay, will always be the same. So from 0 up to 7, this half of the table for ASCII will always be the same. And you've got all your main control characters there, your hash, all your main symbols. Oops, sorry, I keep scrolling past it. But you've got all your, your really important symbols and everything, plus, minus, everything are in the lower half of the table, all right? Now, that's the end of those slides. And all I need to show you next, the one last thing is very quickly to show you the lab for today. And I'm very quick because you're going to be reading that in the lab anyway. So just another couple of minutes. Today's lab is to basically get your LCD, get it connected up, and do some basic experimentation with it. So on the LCD, the controller on the back of it is probably almost certainly a 1602 or 1602A. And these devices are the most commonly used, and they have parallel communication, which means you're sending multiple bits of data at the same time through separate data wires, as per my diagrams we just looked at. Part A is basically look at my code and understand it, so I'll leave you to read that yourself. Part B is to change the message on it. So instead of saying hello from Richard or whatever it said, change the message to be something relevant to your coursework. So you could say on the top line, you could put burglar alarm system. On the second line, it might be enter access code, something like that. That would be part B. Part C is a little bit more complicated. Make a little stopwatch where you're displaying minutes and seconds, or just seconds, and it's counting the seconds. And part D is much more complicated, but nice and interesting, is where you combine your lab from last week with the light and dark from the LDR, so that when it's dark, rather than just your LEDs coming on and off, you actually display the message dark on the LCD, and sorry, on the liquid crystal display, and the message light when there's lots of light on the liquid crystal display. So not too complicated, but more complicated than the other bits, okay? So there's 4 parts. Whatever happens, make sure you get part A and B done, because this would enable you to use it in a simple mode in your coursework if you want to. C and D are more complicated, but you learn a lot by doing them. So obviously try to do them as well. But part B is particularly useful for simply using in your coursework. Okay, sorry that took so long as usual. Any questions?
Nope. No hands raised.
Okay, enjoy your lunch. I'm sure you're looking forward to it, but enjoy the lab even more.
All right. Thank you, Richard.
Okay, see you later.
See you.
Bye.